So yesterday, I believe that we went over ratio. I mean, on Thursday, I believe that we went over ratios and proportions. Um, I'm just gonna go over it one more time before I go on until I go into today's lesson. So it said that a ratio is a relationship between two numbers. So A over B is the most common form used as a fraction. So here 12 feet to 48 feet, that's an example ratio. And whenever you have a ratio, you want to reduce to the simplest form. So 12 over 48, the most simplest form is 1 over 4. So when determining value, you can use ratios. So we're trying to find the dollar per can here. So if there's a pack of 12 sodas and for all of them it costs $3.48. $3.48 goes on top, and you're trying to find the price per soda. So $3.48 divided by 12, and it comes out to be 29 cents per can. Do the same thing for the discount warehouse, 32 cents per can. Proportion. A proportion is a statement of equality of the two ratios. So there's one ratio, there's another ratio, and they're equal to each other. So one half equals 2 over 4. And we know that's true because if you multiply 8 on both sides, multiplication property of equality, then you get the true statement 4 equals 4. So proportions, equality, this is all we're doing. So solving proportions, we cross multiply. For example, 5 over 8 equals n over 4. You cross multiply 5 and 4, and you cross multiply 8 and n. So 5 times 4 equals 8 times n. 20 equals 8n. You divide 8 on both sides. Division property of equality. And then you reduce the fraction 20 over 8. That's equal to 5 over 2 equals n. Applications. Okay, similar triangles. So we have a triangle ABC and triangle RST. Okay, so well, the triangle. So triangle. So triangle ABC and triangle RST are the same, are similar. The angle A and angle R are the same. Angle B and angle S are the same. And angle T and angle C are the same. But for the sides are proportional. So C corresponds with T. So C over T, B over S, and A over R, they're all proportional. The fractions are equal to each other. So that's what we said last time. The first letter goes with the first letter, second with second, and third with third.
Yeah.
Okay. So I went over guided examples. Okay. Did anyone have any questions about ratios and proportions that they didn't have time to ask? If you do, then type in the chat. Okay, sorry, I had a little interruption. So no one had any questions? Type no in the chat. If you did have any questions that you forgot to ask me yesterday, on Thursday, then you can type it in the chat. Ratios and proportions. No? I know the hardest part about ratios and proportions is not solving them, but some of the applications is a little bit difficult to set up, and the similar triangles. So this is important to know. Okay, if you don't have any questions, I'll move on. I can't find it. Oh my gosh. Hold on for a moment. Okay, there we go. So before I move on to today's lesson, which is about linear inequalities, I'm going to go over some of the symbols that are used to denote relationships. We went over this the first week. It's chapter 1. So these are the ones I want to focus on. We use these, but this was for the equations. We're dealing with linear equations. Those are those are true statements. So equal to, the number on the left will be equal to the one on the right. Not equal to, the number on the left is not equal to the number on the right. And approximate equal to, or ignore that for now. Less than, the number on the left is less than the number on the right. Greater than, number on the left is greater than the number on the right. And less than or equal to, this is a statement that is both less than or equal to. You can choose. So let's say that the number here is 6. The number here can be 6 or any number that's less than 6. So 6 is less than or equal to 6. It's equal to 6, so that makes it a true statement. It can also be 6 is less than or equal to 9. So anything on the right has to be greater than the number on the left. So here, the number on the left is greater than the one on the right. So greater than or equal to, 5 is greater than or equal to 5. And 5 is also greater than or equal to 4. So that's how you use these less than or equal to signs. Is there any questions about this? I think we already learned this in class before. If you don't have any questions, just let me know, because we're going to be using these symbols. I want to make sure everybody knows it. Good. Okay, so today's lesson is on linear inequalities. What are inequalities? Algebraic inequality is a statement. So most commonly you have a variable on the left-hand side, and you're going to have one of the symbols, the 4 symbols that I showed you, the less than, a greater than, or less than or equal to, or greater than or equal to signs. And then you're going to have a number, on the right-hand side. So this inequality has infinitely many solutions for x. What does infinitely many mean? There's you can't write every single solution for x. So x is greater than or equal to 2. you just can't write the whole numbers, 2, 3, 4, 5, 6, because you're going to be going on forever and ever and ever and ever. You can't even write the numbers between 2 and 3, because between 2 and 3, you have 2.1, 2.0001, 2.00000001, and so on. So there's infinitely many solutions for x. You just can't write a solution set and put whole numbers inside it. So here they have some examples of solutions that are greater than 2, 2, 3, 3.5, 5, 20, 20.001. So it's impossible to list all the solutions. A system is needed to allow a clear communication of this infinite set. Two common ways of expressing solutions is graphing them on a number line, right here, or using the specific interval notation right here. I'm going to go over what how to use the number line and how to use interval notation. So the first thing I'm going to show you is the number line. So we have 2 here. 2 is included, so x is greater than or equal. So we have the statement x is greater than or equal to 2. So x can be 2, x can be equal to 2, so we circle that in. And all the values to the right of 2 are some values that x can be. So everything greater than 2, including 2, equal to 2, are values that satisfy this inequality. So this is how you use a number line. Let's say, okay, so now we have interval notation. So because 2 is inclusive, okay. So whenever you have interval notation, after graphing a solution set on the number line, which we did here, okay. Inequalities, okay, so whenever you have the number 2, that's the smallest number that that x can be equal to. 2 is the smallest number that x can be equal to. So this is inclusive. Inclusive means that it includes 2. So 2 is included in the solution set. So you have to put a bracket. I'll show you what you do whenever the number is not included. So because 2 is included, you put a bracket. That's the lowest number it can be. So the lowest number on the left is the highest number on the right. So we put infinity on the right because that's infinity is not a number, but it's just the concept that infinity is the upper bound to all real numbers. But it itself is not a real number, but we just put infinity there because it represents that it goes to the right forever and ever. So because this is going to the right forever, we just put infinity over here. Infinity is not a real number, so we can't put any brackets. You can't put any brackets. It has to be a parentheses. All the time if you have infinity, it's a bracket to the right of it. Okay, let's say that, so in this example, we had x is greater than or equal to 2. Before I move on to what we'll do if x is greater than 2 strictly, does this make sense for everybody? I have questions. Okay. So if x is strictly greater than 2, so x is, so you can't have 2 is greater than 2. It's not true. You can't substitute 2 for x and say that's greater than 2. You can substitute here and say that 2 is greater than or equal to 2 because it's equal to 2. But here, this is a strict inequality. So we leave an open circle whenever you're graphing it on the number line. An open circle at 2 and shade in all the numbers to the right of 2. All of these numbers are in the solution set of being greater than 2. So You might notice something different here. Instead of a bracket, there's a parentheses. The parentheses is there because you don't include the 2. It's very close to the boundary point, but you don't include 2. It's not inclusive. So all the time whenever you have something that's not inclusive, the parentheses, use the parentheses. Infinity, we said that infinity is not a real number, so you can't include infinity inside the solution. It's just to represent that it keeps going and going and going. So that's why you put a parentheses around infinity. Put parentheses around 2, parentheses around infinity for strict inequalities. Whenever you don't have the equal sign under the symbol. Okay, does this make sense before I move on to a guided example of how to do this? It's important to understand the concept. Thumbs up? Yeah, makes sense. Good. So before I go to a guided example, I just want to review one more time before I go there. This is a little bit, it's not as easy to understand as the equations, algebraic expressions were. So if it's inclusive, you add a bracket. Infinity never has a bracket, always parentheses. If it's not inclusive, parentheses. Infinity never has a bracket, so it's always parentheses. So in the chat, really quick before I move on, what do you do if a number is not included inside the notation? If it's not included, parentheses or bracket? Yeah. Parentheses. So yes, use the parentheses whenever it's not included. Okay, let's go to a guided example. So here we have an example of an inequality, and they're asking us to graph it and give the interval notation. So here we have a strict inequality. There's no equal underneath the symbol, the less than symbol. So x is less than 3. So all the numbers are less than 3. Whenever you're looking for something less than a number, you're going to the left. You're going to the left of the number. And because it's strictly less than 3, you leave an open circle. Open circle, you don't shade it in because 3 is not included. And because 3 is not included, but 3 is the upper bound for this inequality for this inequality. 3 actually goes on the right because it's the upper bound. Here, 2 was the lowest number, and infinity was the upper bound. But here, 3 is the highest, is the upper bound because it's the rightmost number. So we add 3 here. It's not included, so there's a parentheses. And because it's going forever in the left direction, we put a negative infinity instead of a positive infinity. So negative infinity, parentheses, comma, 3, parentheses. So 3 is not included, negative infinity is not a real number, so it's not included. Does this make sense for everybody? Because we're going to be doing an independent example. Thumbs up, thumbs down. Good. Good. Feel free to ask any question. If I'm moving too fast, then just stop me, okay? Okay. So here, example number 2, graph and give the interval notation equivalent. X is less than or equal to 5. So I use the number line. Use a number line, graph it, and put in interval notation. Make sure to pay attention to the symbol is less than or equal to. When you're done, just type done. Sign off. Once again. Good job, guys. So, yeah. So I'm gonna pick on a random person and explain to me what you did. Yeah. Delina, would you mind unmuting your microphone to show me your steps that you did? Oh, okay. No problem. This one I just go through it myself. So we have x is less than or equal to 5. Because it's less than or equal to 5, we automatically know that it's going to be all the digits to the left of 5. So we can automatically shade, I'm going to use a different color. We can automatically shade all the digits to the left of 5. And keep going in that direction forever. Okay, so now we can put a circle. Are we going to leave the circle open or closed? Of course it's going to be closed because 5 is inclusive. So we said x is less than or equal to 5. Less than or equal to. So 5 is included. So because we said 5 is inclusive, a different color, we can put the bracket, actually. So we're going to put the lower bound on the left and the upper bound on the right. So the upper bound is 5, and the lower bound is negative infinity. So negative infinity is on the left. This is the lower bound because it's going to the left forever. The lowest number, we don't know what the lowest number could be. There's no lowest real number, so we put negative infinity, a concept. And 5 is the upper bound, but it's inclusive, so we add a bracket instead of parentheses. Does this make sense for everybody? We're going to be expanding on this. Thumbs up. Good. Yeah. Okay. Compound inequalities. So a compound inequality is actually two or more inequalities in one statement joined by the word and or. So there's going to be and compound inequalities and or compound inequalities. We're going to treat them differently. There's different things you do for them. So the first one in front of us is a or compounding inequality. x is less than 3 or x is greater than 6. So whenever you have an or inequality, either condition can be satisfied. So all the numbers to the left of 3, not including 3, is a solution set. And all the numbers to the right of 6, including 6, is also another solution set. So these are both solution sets. Both of these are solution sets. How can we write two solution sets if there's an if we're in interval notation? We use this U, it looks like a U, but it's actually represents the word union. So both this solution set and this solution set is true for this inequality. Both of these solution sets are true. So whenever you have an or, you use a union symbol, and you write interval notation for the lower for both of them. So x is less than 3. The lower bound is negative infinity. The upper bound is 3, not included. 3 is not included, so they added parentheses. Infinity is not a real number, so there's parentheses. The upper bound for x is greater than 6 is infinity, all the way down there. So infinity, parentheses. 6 is included because it's greater than or equal to, so there's brackets on the 6. Does solving compound inequalities make sense? I mean, graphing them and writing them in interval notation, thumbs up, thumbs down. I'm going to be going through some guided examples. So, if you don't have your camera on, you can just use the reaction. There should be a reaction somewhere here. Yeah, you can. Good. Okay, so overlapping or inequalities. So sometimes you don't have something clean like this where the inequalities are separated by a space of a few numbers. Sometimes they overlap. So in this example, we have x is less than 3. So they have an open circle, goes all the way to the left. And or x is less than or equal to -1. So closed circle, less than or equal to, all the digits to the left. So there's an overlapping here. Some of the digits that are in the solution set for x is less than -1 are also in the solution set for x is less than 3. So this area is the same. So whenever you have an or statement, instead of writing them separately, you can just combine them to say that with x is less than 3, because all the solution sets for x is less than -1 is included with the solution sets for x is less than 3. So both of these solution sets are combined. So there's no reason to separate them like this. So this is a union of the or inequalities. Does this make sense? Good. Thumbs up. Whenever you have overlapping inequalities, at the same time. Whenever you have overlapping inequalities, you just combine them like this, like so. Independent example. Graph and give the interval notation equivalent for x is less than 3 or x is greater than or equal to -1. Oh yeah, when you're done, type down in the chat. You're done. So this one's a special one. Just make sure to pay attention. Okay, I'm gonna wait for another 10 seconds. Okay. So we're given this problem. Graph and give the interval notation equivalent of x is less than 3 or x is greater than or equal to -1. Okay. So let's say, okay, so we have -1 here. We circle in -1 because it's inclusive right away. So less than or equal to -1. So it's looking for all the values to the right of -1. Yes. Okay, good. Just follow along if you're not done yet. So -1, all the values that are greater than -1, we can shade in. So I'm gonna shade it up at the top because something might happen with the 3, just in case. So it's all the numbers to the right of -1. Keeps going. So 3, we have all the values that are less than 3. So we just go to the left. All the values that are less than 3, shade them in. Okay, so here we have something where so they're overlapping. They're overlapping. This 3 is now included inside the solution set. First it was excluded, but now it's included because of x is greater than -1. So let's substitute. Let's say that you have x is less than -1. Let's substitute x for 3 now. So 3 is 3 greater than or equal to uh, greater than or equal to -1? Yes, it is. It's greater than -1. So that checks out. So 3 is now in the solution set. And all these numbers that were shaded are going in either direction. They're going all the way to infinity. This goes to negative infinity, and this goes to positive infinity. So the number line will look something like this. It's all shaded, and it's going to both to the left and to the right continuously. And the interval notation will look like this. No, keep doing that. So the lower bound is negative infinity and the upper bound is infinity. So it's going to the right continuously to infinity. It's going to the left continuously to infinity. So this is why you have this as your solution, both infinity in the upper bound and the lower bound. This makes sense for everybody? It was a little bit different from what we had before. Good, good, good. Okay, now we have and inequalities. So we're working, yes. Okay, you have a question? Here, I'll unmute you. Ask a question. If you have a question, unmute yourself. Yeah, okay, what's your question? If you don't want to talk, you can type it in the chat.
It was an accident. I
Oh, it was
pressed
an
that
accident?
raise.
Oh, okay. No problem. Okay, so now we have and inequalities. And inequality is a compound inequality. So here we have an example. -1 is less than or equal to x, and x is less than or is less than 3. So we can decompose this inequality to -1 is less than or equal to x, and x is less than 3. So we can decompose these three numbers into an and compound inequality. So the and requires both conditions to be true. So it's not just so for or inequalities, we just had either one can be true. We can satisfy either the left one or the right one. It doesn't matter. But for the and inequality, it's very strict. Both conditions must be true. It must be x must be x must be greater than or equal to -1, and it must be less than 3. So we'll see this. We have this intersection. We'll see this later. Okay, so this is an example of an overlapping and inequality. So it says for you to graph x is less than 3 and x is greater than or equal to -1. This is the same thing that we have here. Okay, so first you graph x is less than 3. So open circle, x is less than 3, all the digits to the left of 3. But we also have x is greater than or equal to -1. So all the digits to the right of -1. But this time we're not gonna have a union. We're not gonna combine them and just say -infinity to infinity. We're not going in both directions because both conditions must be satisfied. So in this uh, in this area are all the solution sets to this inequality, the and inequality. So we have to cut it off where they intersect. We have to cut it off where they intersect. So the intersection is where both values are being satisfied. Cut it off at the intersection. We're not supposed to have infinity to -infinity. And we keep the open circle on 3 because 3 is not included in one of these inequalities. So here, 3 is not included. It's a strictly greater than 3. And x is greater than or equal to -1. So let's take one of the whole numbers here, 0. Is 0 less than 3? Yes, it is. Is 0 greater than or equal to -1? Yes, to the right of -1. Take another number, 2. 2 is less than 3. It's to the left of 3. And 2 is also greater than -1. It's to the right of -1. So this is why you have to have an intersection whenever you have an overlapping and inequality. Thumbs up, thumbs down, questions? Thumbs up. Okay, good. Okay, so here they just explain the answer. This is what it is in interval notation. The lower bound is -1, and the upper bound is 3. So they write it like this. 3 is not included, so they have the parentheses and the brackets on -1. So they just explain whatever I just said. -1 and 3, all the numbers are between it. -1, -0.999, 0, 0.056. So even between this small area, we have an infinite number of solutions, just between -1 and 3. So we can have -1, 0.9999, 0.9999999, 1.000001. All these numbers, there's an infinite, you can put an infinite number of 9s after the decimal point. You can put an infinite number of zeros after 1. So there's an infinite number of solutions, so you still have to write it as the interval notation. Infinite many real numbers between -1 and 3. So here we have independent practice. Make sure to take note that this is not -32, it's -3/2. And make sure to graph it and give the interval notation equivalent. I'll give you some time to do that. Okay, done. I give everybody 1 more minute or go over at 12:58. Okay, so for this question, I'm gonna unmute someone by random. Meraki, do you mind unmuting your mic so that you can show me your steps and how you solve this problem?
Okay. So it's an open circle because it's not equal to anything.
Okay, yeah,
So
good. So
open
open
circle
circle here.
on -3 and 2 and 2, and then I just like they connect like that's
Oh, you connected these?
yeah like in the example you did. Yeah.
Yeah, that's correct. So yeah, if you wanted to, you could have done it like you could have solved them separately. Okay, so let's say that we can decompose this to -3/2 is less than x, and x is less than 2. So we can model this as all the numbers to the right of x. This is the same thing as x is greater than negative 3 over 2. So all the numbers to the right of negative 3 over 2. And for this part of the compound inequality, all the numbers to the left of 2, less than 2. Because it's an and, we need the intersecting part. So yes, you just connect the dots. Very good. So what'd you get for your interval notation? It also says give the interval notation. Marathi. What'd you get for
Well,
your
like
interval notation? You graphed it correctly. This is done. But the interval notation?
you want me to play?
Oh yeah. What'd you do? Did you have a parentheses or a bracket first?
It's a parentheses.
Yes. What's the first number?
3 over 2.
Yes. And comma. You put here.
2
And parentheses or bracket.
parentheses.
Okay, good. You got everything right. So parentheses, because they're both not included, there's no equal to, no equal to. It's just strictly greater. So yes, everything's right here. This makes sense for everybody other than Marathi. Yeah, that's good. Okay. I'm glad you guys are doing it along. I'm not catching anyone off guard. Okay. So I believe it's 101. We'll have our usual break. And we'll resume at 1:10. 1:10 we'll resume. Okay, is everybody back? Type here in the chat if you came back. Here, that's good. Hmm. Okay, so uh, most of this class is for algebra only. I I would have started pre-calculus, but I wasn't able to because most of the people in this class are going to ninth grade or 10th grade. So I'm focusing solely on algebra. But if you need any instruction, you can find some problems, and if you need any help with it, I can help you. I can also tutor pre-cal. Sorry. You're welcome to say if you find this as a review. Okay. Okay, since everybody's back, we're gonna resume. We're halfway done. So linear inequalities. A linear inequality is a mathematical statement that relates to linear expressions as either less than or greater than each other, and then another. So last time we were working with linear equations. Not last week, but I think Tuesday last week. We're working with linear equality. Yeah, equations and inequalities. So they're in the form y ax plus b equals c. But here we have ax plus b is less than or greater than, or less than or equal to or greater than equal to c. So these are all examples of linear inequalities. The steps to solve linear inequalities are pretty similar to the ones that we use to solve linear equations. You use the properties of equality to isolate the variable term. Then you use multiplication or division to isolate the variable, and then you just simplify. So just so let's see what the solution to linear inequalities look like. So here we have a linear inequality. 3x plus 7 is less than 16. 3x plus 7 is less than 16. Okay. So they're asking if x is a solution, x equals -2 is a solution to 3x plus 7 is less than 16. What can we do? We just substitute x for -2. So 3 times -2 is -6. -6 plus 7 is 1, going to the right 7. So 1 is less than 16. Is that true? Yes, it is. So -2 is a solution for 3x plus 7 is less than 16. Let's see if 4 is a solution. So you plug in 4, 3 times 4 is 12. 12 plus 7 is 19. 19, is 19 less than 16? No, this is a false statement. But this is not a solution for 3x plus 7 is less than 16. So to check if one of your solutions is correct for an inequality, you can just plug it in most of the time. If you have time left in a test, then you want to make sure that something's right, you can do this. Plug in the number, and if it results in a true statement, it is a solution. So this is how you identify solutions for inequality. So these might look pretty similar because we did go over this before. These are the properties of inequalities. Last time you saw something like this, it was the properties of equalities. But this time, because we're dealing with linear inequalities, you have pretty much the same properties, but there's some key differences that you have to know. So for addition, the same thing. Whatever you add on the left, you add on the right. So they added the variable c. left and right. Subtraction, same thing. Whatever you add on, subtract on the left, you also subtract on the right. For multiplication, positive number, whatever you multiply on the left, you also multiply on the right. But if you have a negative number, this is important to note. If you multiply a negative number on the left, and you also multiply the same negative number on the right, but you have to flip the sign. So before it was A is less than B. Now it's negative C, A is greater than negative C, B. You have to flip the sign. If you don't flip the sign, the whole thing will be messed up. Same thing for division. Whatever you divide on the left, you also divide on the right, positive C. But it's a negative. If it's a negative C, you divide negative C on the left and the right, but you have to flip the sign. Make sure to flip the sign. If it's a less than, turn into a greater than. If it's a greater than, turn into a less than. So here we can apply some properties of inequalities. There's no variables here, but they're just playing with it to show you that if you subtract something on the left and you subtract something to the right, it's still going to be true. So they subtracted negative 7, both on the left and right. 10 minus 7 is 3. Negative 5 minus 7, you're going to the left 7, is negative 12. There's a true statement still, just like this is. 10 is greater than negative 5. 3 is less than negative 12. So here they have 10 is greater than negative 5. So they divided 5 on both sides to show the division property of inequality. Divide 5 on the left and 5 on the right. 10 divided by 5 is 2. Negative 5 divided by 5 is negative 1. This is still a true statement, just like this is. So you can use the property of inequalities to manipulate the equation. So here we have an example of solving an actual linear inequality. It looks very similar to an equation. You could have pretty much put an equal sign over here, but sometimes we have to put the sign so we keep it here. So 3x plus 7 is less than 16. It looks familiar. Yeah, we have it here. So 3x plus 7 is less than 16. 3x plus 7, we want to isolate the variable term, so we subtract 7, bring it to the right, all the constants on the right. So negative 7, subtract on both sides. 7 and 7 cancel out, so 3x. 16 minus 7 is 9. So we isolate if we want to isolate the variable term, we use the division property of equality. When we're dividing a positive number, the signs stay the same. Divided by 3, divided by 3. So x is less than 3. They also ask for you to graph the solution. So it's an open circle. It's not inclusive, so open circle. And all the values to the left. If it asks for interval notation, you can say that it's a parentheses, negative infinity, comma, 3 parentheses. No brackets. If they ask, but they didn't ask for it, so you just have to graph it. So here, it's just taking note of the key difference. If you multiply something on the left, that's a negative, and you have to multiply the same negative on the right, but you flip the sign. Same thing with the division. Now, before I move on, did everything about linear inequalities, the properties of the inequalities, and applying them make sense? Thumbs up or thumbs down? Good. Thumbs up. Okay. So this is another solving in linear inequalities. So we'll go over this. Solve negative 2x plus 1 is less than or equal to 21. So negative 2x plus 1, they wrote it again. So the goal is to isolate the variable x. Subtract 1 to get the variable term by itself. So 1 minus 1 cancels out the 1. You bring the constants together on the right-hand side. So negative 2x is greater than or equal to 20. So we still want to isolate the variable x. So we can use the division property of inequality, divide -2 on both sides. But we have to remember that whenever you divide a negative, both sides, you have to flip the sign. So that's what they do here. They flip the sign. It's still equal to, but they just flip the sign. So it used to be greater than or equal to, now it's less than or equal to. So the -2's cancel out, and you're left with x is less than or equal to -10. They only ask to solve for it. This is how you this is the answer. X is less than -10, but you can also express it through a graph. You have -10 here because -10 is inclusive. Then you shade it in. It's a closed circle, and shade in all the values to the left of -10, going to infinity. You can also express it in interval notation. Negative infinity, parentheses, comma, -10, bracket, inclusive. This makes sense? Thumbs up. Okay, I'm glad everybody understands it. So now, it's your turn. So I can solve this independent practice. Give you a few minutes. Okay, good. I'll wait a little bit. Okay. I'm gonna wait another minute. No. Okay, so it's 1:24. I'm gonna ask someone to unmute their mic. Mikias, do you wanna unmute your mic so that you can show me how you did this? I'll
So
guide you through.
do
Okay.
I just do I do like the steps, or I just say the
Yeah,
answer?
just say what you did.
So basically, the times -7 with 2x, you get -14x, and then times -7 with 1, you get -7.
So you
Add
distributed, okay.
yeah, distribute it, and then add 7 to other side, 8. Then you divide -14x to other side, which is x, and like the equality switches to x is greater than 8/14, and you simplify x is greater than 4/7. Wait, was I supposed to graph it?
No, it just asks for you to solve. But if you were to graph it, what would you do?
You would just you place negative 4/7, positive 4/7, put a circle, and then the x will go to the right.
Okay, good. Interval notation, what would you do if they asked for that?
It'll be parentheses 4/7, and
4/7. Be careful. So
for
you're going to the left. You're going to the left. So what's the lower bound? What's the lowest number? If you're going all the way to the left continuously. Sorry.
Wait, I'm confused.
So you're going all the way to the right.
Yeah.
So yes. And what would be the right?
And the right will be infinite sign.
Okay.
Is that me?
Thank you.
Welcome.
So yes, just for if I was going too fast, you distribute the -7 to the 2x. You also distribute the -7 to 1. So -7 times 2x is -14x, and -7 times 1 is -7. And you want to isolate the variable term, so you add 7 on both sides to bring the constants on the right side. So let's add 7. 7's cancel out. 1 plus 7 is 8. So you want to isolate the variable now. So you divide both sides by -14, the division property of inequality. The -14's cancel out, so you're left with x. We flip the sign because it's a negative symbol. So we flip the signs. So x is greater than 8 over -14. So we can reduce this fraction. It's not in the fully reduced form. You can divide each side by 2, and you get 4/7, -4/7. So that's the answer. If they ask for you to graph it, this is how you would graph it. -4/7, open circle, and shade in all the numbers to the right. And if it asks for interval notation, then parentheses -4/7, infinity symbol, parentheses. Thumbs up, thumbs down. Is good. Makes sense. Okay. So you can also solve compound inequalities. So we're just solving regular inequalities with only one statement. There's no or and. So here's some examples of compound inequalities. This is an and statement where we can decompose this to 2x. Okay, we'll get to that. You can decompose this to an and statement, both of these. And this is an or statement separated by the word or. So either of the inequalities has to be satisfied. So this one can be satisfied or this one can be satisfied. Both of the values do not have to be met as an and only. So if you have an and inequality like this one is shown here, -3 is less than 2x plus 5, and 2x plus 5 is greater than 17. So you can decompose it to that. -3x is less than 2x plus 5, and 2x plus 5 is less than 17. So you can decompose this to an and statement. Just ignore the -3, write the 2x plus 5 is greater than 17, and then you can ignore the 17 and write -3 is less than 2x plus 5. So you can solving these and inequalities is pretty easy if you decompose them. But you can also solve them without decomposing them if you wanted to. It just requires a lot more. You got to be precise. So you want to isolate the variable x. So you divide subtract 5 on in the middle term, the left term, and the right term. So you subtract 5 on all of the terms. Whatever you do to one, you do to all. So then after subtracting 5 to all the terms, the 5 cancels out, and you're left with 2x in the middle term. In the left term, you're left with -8. -3 minus 5 is -8. And 17 minus 5 is 12. So you have 12 in the right term. You still want to isolate the variable x. So you divide 2 to all the terms. Divide 2, divide 2, divide 2. The positive number, so you keep the signs the same. The sign's the same. And -8 divided by 2, -4. The 2's cancel out, so it's x. And 12 divided by 2 is 6. So you're left with the and inequality. -4 is less than x, and x is less than 6. So if you wanted to graph it, you take the intersection, -4, 6, intersect them, and have open circles because it's non-inclusive, no equal signs. And interval notation, again, there's no inclusive, so just parentheses. And for -4 is the lower bound, and 6 is the upper bound. The solving and inequalities makes sense because we're going to do independent practice. If you have any questions, you can type it. Okay, here's the independent practice. Make sure to note that the small 1 and 2 is 1/2 instead of 12x. So okay. Gonna wait for a little bit more time, about a minute. Okay, so I'm gonna go over question now. As usual, I'm gonna unmute someone. Abel, do you mind unmuting your mic and showing me your steps?
Hello.
Yes, hello. Can hear you. So what'd you do first? Hello?
First, first, I basically like split the equation. That way I could
Yeah,
solve
that's,
the
yeah,
above.
you can do it that way as well. That's good. So what'd you split it to?
-1 is less than or equal to 1/2 x minus 3, and then one 1/2 x minus 3 is less than 1.
Okay, so want to do this one first or this one first?
Doesn't matter.
Okay, so the left one, what'd you do?
First, I multiply everything by 2 to get rid of the fraction.
Okay, okay. Now what'd you do?
Then I subtracted. I added 6 on both sides.
And addition, properties, and inequalities. So 6 minus 2 is 4. And so this is done. Now this one, what'd you do?
Multiply everything by 2 to get rid of the fraction again.
Okay. Okay, so what'd you do now?
And add 6 to both sides.
Okay, so now you have this. That's it. If you wanted to graph it, okay, so would you have an open circle or closed circle of 4?
Closed.
Closed. And then at 8, closed or open?
Open.
Open. So 4, at 4, would you be going to the left or to the right? Would you be shading numbers to the left or the right? Because here we have 4 is less than or
To
equal
the
to
right.
x. To the right?
Yes.
Okay, so this is the same thing as x is, sorry, x is greater than or equal to 4. Same thing as this. So yeah, we're going to the right. For 8, it's less than, so we're going to the left, right?
Yeah. Yes.
Okay, yeah. All right. So going to the left. So it's just this intersection right here. That's how you graph it. If you were to do it in interval notation, what would it be on the left hand side? Would it be a bracket or parentheses first?
Bracket.
Then we put 4, uh, parentheses or bracket.
Parentheses.
Okay. Number line, interval notation, and answer. These are all the forms that you can express your answer. Most of the time, they only ask for one in the test. Okay, solving OR inequalities. So we solved an AND inequality earlier. I have an OR inequality. This example, solve 3x plus 1 is less than 10, or 2x minus 1 is greater than or equal to 11. So these are already decomposed, so you can just solve them the way that they are. Just go down, solve the left one first and the right one next, or you can solve the right one first, but it doesn't matter. Just solve each of them separately. Then once you find out what your answer is, you have x is less than 3, or x is greater than 6, greater than or equal to 6. This is your answer, the one that you get at the bottom. You just bring the or all the way down. So isolate the variable term, subtract 1 on both sides, subtraction property of inequality. You end up with 3x is less than 9. So you want to isolate the variable x, divide each side by 3, x is less than 3. Over here, add 1 on both sides, subtraction property of equality. Negative 1 cancels out, so you're left with 2x is greater than or equal to 12. Divide both sides by 12, and you're left with x is greater than or equal to 6. So if you want to use a number line to express your answer, open circle at 3, there's no equal to, it's non-inclusive, and then you shade all the numbers to the left of you. If you, you look at 6, it's inclusive, so it's a closed circle, and all the numbers to the right. It's not in space, so it's just cut off. Interval notation. Remember the union. Because there's no intersecting, there's no overlapping over here. We have to use the union symbol. So all the values between negative infinity and 3 union with the 6 and all the values to the right of it, 6 to infinity. So you have to use the union whenever there's a gap like this. Make sense? Thumbs up, thumbs down. Good. So linear equation and linear inequalities are just like linear equations. There's also going to be word problems. So it's important to note these key words and phrases that indicate inequalities. So just like we had the operations we saw, you can convert the words into math. You're gonna have to do this for word problems, converting the expressions into algebra. A number is at least 5, so at least meaning that it's greater than or equal to 5. Number is 5 or more inclusive, so it's including 5. You have to have a greater than or equal to sign. A number is at most 3, so it's at less than or equal to 3. So you're going to be dealing with at most when you're having budgets. At most, you're going to be purchasing with $25, something like that. A number is 3 or less inclusive, so whenever you have inclusive, you have to make sure to have the equal sign. A number is strictly less than 4, so the strict inequality, there's no equal sign, Same thing with non-inclusive. When you have non-inclusive, there's no equal sign. Numbers greater than 7, yeah, that's just a symbol you're converting into translation. A number is in between 2 and 10. So whenever you have something that's in between, the x is your number, in between 2 and 10. So x has to be greater than 2 and less than 10. So this is where you can use a compound inequality to represent something where a number is in between. You can also use a compound inequality when you're asking if a number is at least 5 and at most 15, so less than or equal to 15 and greater than or equal to 5, at least 5, at most 15. And the number may range from 5 to 15, the same thing. So it could be 5, it could be 15, and it could be all the numbers in between. So x is in between 5 and 15. This makes sense? Key words, word problems. It's almost like the linear equations, but it's the symbols instead of the operations. Here we're going to be looking at an example. translate 5 less than twice the number is at most 15. So, the 5 less than twice the number, we've seen this type of thing before. So twice a number. So a number, that's our variable where we don't know what the number is. So they use the variable n. So the n times 2, the coefficient 2. So 2n, twice the number, less than 5 less than. So subtracting 5 from it is at most 25. So whenever you have at most, we're using a less than or equal to. Less than or equal to at most. If it's a greater than or equal to, then it's at least. So 25. Thumbs up, thumbs down. Good. So we're gonna have another example. This is a little bit more complicated. The temperature in the desert can range from 10 degrees Celsius and 45 degrees Celsius in one 24-hour period. For those of you who don't know, that's a very big range. Okay, when they solved it, they got 50 to 113. So it can be almost freezing, you're very shivering, to it's sweltering, you're sweating a lot in the desert. Many people don't think that the desert can get that cold. So it's asking for the equivalent range in degrees Fahrenheit. Given that C is equal to, this is, well, 5 and 9 is 5 over 9, F minus 32 in parentheses. So you set up a compound inequality. So you're trying to find the temperature in the desert. It's a range. So we said that the number may range from this number to this number. Whenever you have a range, you put the variable where you're trying to solve for in the middle. This is the temperature in Celsius. We don't know. We're trying to find. My connection's unstable. Okay, so our unknown goes in the middle, and 10 and 45, that's what the numbers can range from. The number can be greater than 10 and less than 45, or equal to that. So the temperature in Celsius, so we said that temperature in Celsius is equal to 5 over 9 F minus 32 in parentheses. So this is the temperature in Celsius. This is how you can convert it to Fahrenheit. So this is the temperature in Celsius. Whatever the temperature in Celsius is, you can use this to convert it to Fahrenheit. But we want to solve this for F. You want to solve this for F. The first thing you can do is get rid of the fraction. How do we get rid of fractions? You can multiply by its reciprocal. A reciprocal, again, is flipping the fraction. So from 5 over 9, we can convert it. 5 over 9, reciprocal of 5 over 9 is 9 over 5. So 9 over 5 times 5 over 9, cross multiplication, whatever, is just 1. Anything times its reciprocal is 1. So 9 over 5, whatever you do in the middle, you have to do to the left and the right. So 9 over 5 times 5 over 9 cancels out. 9 over 5 times 10, that's equal to 18. 9 over 5 times 45, that's equal to 81. So you're left, because you got rid of the fraction, there's no more parentheses inside. So you got rid of the parentheses. The next step is to isolate the variable f. So whatever you do in the middle, you do to the right and the left. Addition property of inequality. So you add 32, 32's cancel out. 81 plus 32, 113. And 32 plus 18, 50. So the temperature in the desert ranges from 50 to 113 degrees Fahrenheit. So what they did, the most important part, again, all the time, is setting up the inequality. That's the hardest part. Easy part is just doing the algebra. So does this make sense for everybody? I'm gonna do a guided independent example soon. Good. Thumbs up. So yeah, temperature in Celsius, you're trying to find it. They gave you how to calculate convert the Celsius to Fahrenheit. So C, temperature in Celsius, we can just put. Okay, so here's an independent example. In the first 4 events of a meet, A gymnast scores 7.5, 8.2, 8.5, and 9.0. What must she score on the fifth event to average at least 8.5? So remember that average is the sum of all the numbers divided by the number of numbers. That doesn't make the wording's a little whack, but uh, there's supposed to be 5 events, so you divide everything by 5. So the average is defined as the sum of all the numbers divided by the amount of numbers that there are. So there should be 5, so you divide everything by 5, and you're looking for what the last event is. Okay, so I'll leave you to it. I'll give you a few minutes. You think you got it? Good. Make sure to check it or give everybody some more time. 154 will go over. Good. Okay. So it's been a few minutes. For the sake of time for this one, I'm just gonna do it by myself, but just follow along. So the gymnast scored 7.5, 8.2, 8.5, and 9.0. So these are the times we're given these times. What must she score on the fifth event? We don't know what the fifth event is, so we could just say it's X. We don't know what she scored on the fifth event, it's X. but we need to know that the average is 8.5. So for an example, I just put here that the average or mean is a different way to say average, is the sum of the numbers a plus b plus c divided by the amount of numbers that there are. So there's 3 numbers here, so divide by 3. For this one, there's 5 numbers. 1, 2, 3, 4, 5. We don't know this one, but it still counts as a number. So 7.5 plus 8.2 plus 8.5 plus 9.0 plus x, all divided by 5. The average must be 8.5. So what do we do here? The first thing we want to do is get rid of this fraction. So we just multiply it by 5 so that it cancels out. It cancels out. So we're left with 7.2 plus 8.2 plus 8.5 plus 9.0 plus x equals 8.5 times 5. Okay, let me just bring out the calculator for the sake of time. So we wanted to know what 8.5 times 5 was. 8.5 times 5. So you have 42.5. And let's just add all the numbers, all the scores, so that's easier. 7.2 plus 8.2 plus 8.5 plus 9.0.
Wait, wasn't it 7.5?
Yeah, sorry, 7.5. Sorry. So we get 33.2. So 33.2 plus x equals 42.5. So we could just use sorry about this. Let me just address this really quick. So instead of an equal sign, it says at least 8.5. So at least 8.5, whenever we have at least, it has to be greater than or equal to. Sorry about that. Greater than or equal to. Greater than or equal to. So we subtract 3.32 on the left-hand side and the right-hand side, subtraction property of inequality. We don't need a calculator for this. 5 minus 2 is 3. 12. 12 minus 3 is 9. So 9.3. X is greater than or equal to 9.3. So she has to get a 9.3 or greater on her fifth event to average at least 8.5. So she has to do really good. So this is how you solve this. I have another question, but I'm not going to do it. If you have a phone, you take a picture of this last example. It'll just be homework. It's very simple. You can do it in 5 minutes or less. If you're using a computer, there's something called snipping tool. You can use the snipping tool to crop the picture of it. Whenever you're done, just say done, and I'm going to transfer the host to the audio. Thank you guys. Done. Thank you guys for joining me. I'll make sure to come on Thursday, same time, 12 to 2. Thank you and bye.
Thank you.
Thank you.
Thank you.
Salam.